think on the contrary, we may have much less time for optimization because, so by the time you optimize your software use cases and et cetera, for one system, the people may move on to the next system already. So what do you think about that?
That's actually historically been a big problem, right? Because more, as you sit and optimize and work really hard on that, Moore's law comes along and swamps you every couple of years, or at least it used to. And I was actually hopeful when, we're starting to see sort of fixed clock rates and, just more cores, sort of a slowing of that we'd actually have some time to catch up on sort of software optimization. But then we've had this AI explosion that's thrown all into chaos. But I do think, look, again, the estimated AI infrastructure spending is $400 billion this year. And most of that is in the private sector, and most of them have CFOs that will eventually ask the return on investment question. Remember that $1 billion we spent on AI infrastructure last year that you're asking for $1 billion more this year? What do we get for that? And at some point, this pace will slow down. So, there's still going to be fairly significant infrastructure, but when we get out of I must be the first 5 trillion parameters, first 10 trillion parameters, and I don't care how much it costs to get there. At least, we'll still have the problem that new hardware is going to come along pretty quickly, but I think we can at least, take some time to sort of go through and optimize some when we start thinking about the return on investment and cost. And I think the good news is for things, we're making this huge shift right now, everything GPU centric. I mean, let's say these, broad NVLink fabrics become the way to go. It's less dramatic to go sort of from one generation to the next, right? So the things we learn optimizing Blackwell NVLink will carry on to Rubin NVLink, and maybe somewhere we'll start saying, hey, if one in the next generation, we need more of this or less of this, and sort of co-design our way forward and guide some of that. So yeah, it's always going to be a race. We're never going to optimize as much as we want. It's never sexy to sell software optimization from a funding perspective versus the next architecture. But I do think it's been such a blinding rate of change that we need to catch up some on this stuff.
Any other questions? Any questions from online? No? Okay, so then let's give a big hand again for Dan.
I'll send you this year's slides. Thanks, everybody.
Yeah, okay. So thanks again, Dan. I just want to add a quick comment. I mean, all these complexities are coming up. We love it. When the students see that this is NVL72 with 11 interface, there lies a supercomputing paper, okay? But we need access, okay? So if you give us access, all these students who are sitting there are excited. They will work and optimize, and you will see a very good, nice paper, okay? But that's what we have been doing over the years, but I just wanted to indicate that. So, so here I'll just try to provide you an overview of the MVAPICH project. Those who are familiar or those who are not familiar, I'll start with that a little bit, and then go into like, what are we working on? What are our roadmaps? So if you take a very broad look, like the field, how the field is changing, like 1975, we started with scientific computing. Then in another 25 years, the big data analytics came, but of course, now we have all the AI. So that is leading to this convergence kind of things. If you take any real workflow, people are not doing things in silo. Like might be in that workflow, you may try to do a HPC for some part, or AI followed by analytics, so go back and forth. So in that context, what we have been trying to do in the last several years, we are trying to change the directions in our research group, saying, because we have invested a lot on the MVAPICH, MPI software stack, can MPI-driven converged middleware be designed? Okay, so it will the same MPI runtime, because it doesn't matter whether you're running AI workload or Spark or big data, any of the workload, the upper interfaces may remain the same, but you still need to execute the same thing on the CPUs, GPUs, interconnect. Okay, so the communication is there. It's not like communication is vanishing from the big data or AI workload. So that's what we are trying to do, and I'll try to show you where we are heading in that direction. So this is what will be the outline. I'll provide a very brief overview of the MVAPICH project. And for the last few years, we have been bringing this new MVAPICH Plus series. And actually, this is based on the feedback from this Merck community. I'll show you how we have converged on that. And then I'll try to show you some features and performance of the MVAPICH Plus 4.1 that converts software stack. And one of the features we have been heavily investing these days on the on-the-fly compression for GPUs. And then I'll be trying to show you that converged stack. Yesterday, you saw some of those things from the tutorial. Using the same MVAPICH Plus, we have connected the PyTorch, very latest version, and then you can actually run all your training without nickel, without RICL, or without any of the XCCL, okay? Because the MPI library will try to provide you exactly the same collectives, all reduce, all to all, scatter gather, you all gather, but with a good performance. And then I'll talk a little bit about the issue micro benchmarks. We are trying to steer that a little bit in a different direction now, and then some of the upcoming features, and then I'll finish. So this is what, if those of you don't know, we started this project almost the day one of InfiniBand, when InfiniBand was introduced in October 2000. Prior to that, we were working with Quadrix, we were working with Miricom. I think that's what I told Rich. I met Rich when he was at Los Alamos National Lab. We were working on Quadrix. We actually worked with them, optimized their MPI stack. I think whatever that LA MPI stack, right? Los Alamos MPI stack was there. We worked with him to optimize on the Quadrix itself. Okay. So then, of course, the InfiniBand came, and when the standard was introduced, of course, there is a lot of announcements and all, but there are no softwares to really run on that. So we're the very first one in the world to jump in and started working on it. Okay, and I think I have indicated this anecdote. I went, I think, Rich, you might be knowing Mark Schulzberg, who was the VP that time. I went to his office in San Jose, and I said, look, I want to do some work on this network. He asked me, what is your business? I said, I don't have a business model. Okay, I don't have any business. So he was totally surprised. He was VP sales that time. So he wanted why I'm here. Okay, so then I told him, I gave him some perspective, what we do and all. So that's how we got one SDK, okay, in the very beginning. And then since then, we started working on all these things. We had actually the first open source thing, if some of you remember, at 2002, supercomputing in Baltimore. We actually demonstrated it first together with Mellanox that time. And it was only 8-node InfiniBand, okay? And it was very hard to make it run. You know, the early stage of the network technology, it was very hard to run it on the execution floor, but now we have come a long way. So with that, not only we started with the InfiniBand, but we have been growing, expanding into all the different interconnects. Now we support all the interconnects. We also have this OSU micro benchmark. I'll talk a little bit. So I'm very proud of my team. We have been able to run it for 24 years now with a lot of students, staff, funding. And currently it's being used by more than 3,400 registered organizations. So you can take a look at them from the MVAPICH page. And as of this month, we crossed 1.93 million downloads just from our website. Okay. Of course, we are a part of OpenHPC, SPAC, Red Hat, SUSE. It's very hard to keep track of those, but these are directly downloads from our site. And of course, we have been in the field, just like Dan said, we have been a partner for TAC for the last 19 years. Similarly, we work with a lot of DOE labs, HPC centers all over the world. So this is what it just quickly tells like all our releases, how the downloads have been going up every year. But this is the overall architecture. You saw a little bit of that yesterday. So this is the very latest. We started with here. If you see this part is the network. So MVAPICH is a derivative of MPICH. So we have the latest version is the CH4 netmod. So this is where we support all the different networks, okay? And the transport protocols, and this side is the more CPU, GPU, DPU, etc. But the middle part is the research. That's what we carry out in our group. So when I said before the talk started, when we see a very complicated architecture, this is where like a lot of challenges, opportunities exist. So we try to look for all these like a point-to-point collectives, fault tolerance, what are the new things, what is coming. And then of course we publish. But what we have done over the years is convert those publications to real software. Okay, it is not easy. Those of you who have been in this field, and that too in an academic setting is very hard. But we have been able to do that. Again, I'm very proud of my team. Over the years, we have been able to do that. And then, of course, we started with MPI support. Around 10 years back, there was a lot of actions on PGAS. It is still there. Hybrid PGAS, it is still there, but not in a big manner. So that's what we have been doing for the last several years. But in addition to like supporting HPC, as I said, like now we are gradually same stack you can see, but we are trying to link it with the machine learning workload, like the PyTorch or big data, like Spark can now run over MPI, DAS can run, all those like other stacks also can run. So the idea is that if we invest on these and optimize all these lower layers, we are able to actually provide good performance to the upper layers. Okay, so that is the kind of the direction what we're going. I also want to indicate here, like we do a very rigorous testing when we release. For every kind of like a test here, you will see the different kind of the OMB, IMB, MPICH test suite, Intel. Almost like you can think of like spend about 18,000 core hours per commit. Okay, before we go into the actual testing, release, performance regression. Also, we do application-based evaluation. We have a lot of remote access to many systems like TAC and other places. Once we finish our systems, OSC also, we use a lot of OSC machines to do our testing. So gradually we start from like a small and then gradually go and large ones, and then we make the release so that you feel comfortable in actually downloading and running. So that's the ecosystem under which we have been running over the years. So let me go into the new series. So this is a little bit of historical perspective. We started with MVAPICH. At that time, it was identified as MVAPICH 1. Okay, I mean, it was MVAPICH, there was no 1, but by default, like people considered it MVAPICH 1. We started with InfiniBand. Actually, those of you who don't know MVAPICH acronym, it has been very uniquely designed. Okay, we're a derivative of MPICH, so MPICH is there. Mellanox initially had verbs level API called VAPI. Okay, so that's how that V came. Okay, and at that time also, Lawrence Berkeley National Labs, prior to InfiniBand, there was another technology called VIA. How many of you know? Virtual Interface Architecture. Those of you? So they had a MVICH, MVICH. I don't know whether you know that. So like this, a lot of this knowledge came and we wanted to give credits to everybody. Okay, so that's how the MVAPICH was coined. Okay, so we started with verbs, then gradually PSM came, QLogix, then iWork came. So like this, we continued on that MVAPICH 1 series for some time, 2003 to 2010. But then the new MPICH 2 standard came, MPI 2.0 standard came that had one-sided operations and all. Gradually, people wanted to move. So that's where the MVAPICH 2 started. Okay, and over the years, as we started MVAPICH 2, so of course, those got deprecated. But the most important thing came with this GPU direct RDMA, which is a very common terminology these days, whether in the AI world or the HPC world. But you go back in 2011, 14 years back, that was the very first technology which came. So we were actually in a three-way collaboration between Mellanox, OSU, and NVIDIA. That time they were not separate. They were not together. They were separate. So we brought that GPU direct RDMA. The driver support was done by Mellanox and NVIDIA, but we brought the MPI support. So that is where in the 2011, if you go back, it was an ISC paper. We really showed like you can do GPU to GPU data transfer in 1.2 microsecond. Okay, so this of course then continued. So then the GPU became so quickly. What happened is we wanted to support the community, so that's how it got bifurcated. Like we had an MVAPICH to GDR for GPU. Then we had actually the, if you remember, like the AWS had their elastic fabric adapter. People wanted to run things there. So we had an optimized version for EFA. So like this, we got very quickly, there were multiple different versions. And then at that time, at this mug, if you go back and look at some of the presentations, people indicated there are so many versions, it's becoming really hard to deploy, saying that, okay, can you really unify all these releases into one thing so that it will simplify the installation, deployment. So that's the feedback we have been taking. So that is where this new MVAPICH Plus came, so that now we have actually two versions. There is an MVAPICH, there is an MVAPICH Plus. Okay? MVAPICH is the open source, MVAPICH Plus is like a closed, but it's available. And this I have indicated earlier because we bring a lot of newer designs. Technology is moving so fast, we need to protect the IPs of the student's thesis. That is the most important thing. I mean, because otherwise, as soon as you make it open, in 3 months, other people are trying to copy it, it becomes very hard to publish. So all the thesis, so that's what we do, like MVAPICH Plus is our close, but you can use it. And over the years, as the papers have been published, the technologies are matured, students have graduated, we gradually push things to the back to the open source. But both versions are free, and then you can actually use. So then recently, this is that converse software stack. So let's say we have MVAPICH library, we support all the CPU, GPU, DPU, IPU, you name any of the interconnect. So the idea is that can we have, in addition to the HPC support, can we provide AI and big data? So in that way, we can actually try to provide whatever investment we are trying to do in the API layer, we can actually try to deliver that also for the scaling and performance, portability for the other workload. But this is very important. That's what I want to highlight. So these days, if you go through commodity clusters, okay? So I think Dan indicated in some of his slides. So let's say you take 3 CPUs, AMD x86, Intel x86, and ARM. There are 4 interconnects. Major ones I'm saying, again, there are more, is it InfiniBand, Slingshot, OmniPath, and let's say Rocky. 3 GPUs or 2, you can say, NVIDIA, AMD, and Intel. So if you do a quick math now, it's 36 combinations. So if an end user wants to deploy a cluster, obviously the end user is trying to say, okay, how do I minimize this for my workload and all? But then the question is, who supplies the software stack for this? Okay, all combinations don't come from the vendors. Okay, so somebody might be using a Slingshot as an interconnect, but AMD GPUs and ARM CPU, right? That is a valid combination. But who will provide the software support there? So this is where I think we are trying to, MVAPICH project is trying to make sure that we remain vendor neutral. So we are not favoring any vendor, but given access, provided we have access, we know the designs, we will be able to optimize MVAPICH. So that actually provides to the user base the complete flexibility. Okay, so you should be able to actually get it, and not only for the on-premise, also but for the cloud. So, so that has been our very broad goal, and that's what we have been carrying. As long as we have funding, we have students, we'll be able to continue on this. It's not free. Okay, I mean, there is always behind the thing, there is a lot of manpower and effort listed. So that's what led to this MVAPICH 3. But then another interesting thing happened, if those of you are familiar in this field or know the field, we had this Open Fabrics consortium, am I right? How many of you know that, Open Fabrics? Okay, many of you participated. So we had all the people, like it started with OpenIB in 2000, 2002. Then iWork came, they become Open Fabrics, and people were continuing. So that was the stack, and we are building MVAPICH on top of that, so you can use it for any network. But in the last, 7-8 years, the community got bifurcated. Open Fabrics don't exist. And that led to these two things, UCX and OFI. The two different communities nowadays. UCX is mostly being driven by NVIDIA, and then OFI is being driven by Intel. So then what happened, we quickly moved because people wanted like some interconnect like Slingshot. I know Keith is here. It was only available through OFI. So unless we provide an OFI support in MPI, then it will not run on Slingshot. All right, because Slingshot is not exposed at the lowest layer. Okay, I think it is still, that assumption is still correct, right? You cannot do at the below Wi-Fi, we cannot go, unlike the InfiniBand. So then what we did is, this was our 3 series, MVAPICH and MVAPICH Plus 3. So quickly we moved our design to run on UCX and OFI, the basic versions. But then whatever we had worked on, a lot of these earlier designs were not there. All those optimizations we couldn't quickly bring. So gradually we are trying to bring. So that's what is like the MVAPICH 4.1 series. It is still based on UCX and Wi-Fi, but gradually we have started bringing some of those earlier designs. And then as we move along on the 4.x series, you will see more and more features. Whatever we had here, we'll be able to move it here. Okay, so that you can get both the performance and at the same time you'll be able to run on all the different interconnects. So let me go into a little bit detail. So this is our GA release, very latest GA release. I think last month we released it, and this actually, so now it has GPU support. This is our, like you can think of the very advanced version. It has all the GPU support, maximum of the old features. We support both Wi-Fi and UCX. So now you can actually see it supports any combination of CPU, GPU interconnects. I'll talk about a little bit of support for adaptive dynamic tuning. This you heard yesterday. There's a very new feature we are introducing. And then, of course, the CUDA-aware MPI has been there, starting from the GDR, but now we are focusing a lot on the on-the-fly compression. I'll also talk about that. So the way we call it, like this is our base module, then we have all these advanced modules. Okay, these are for the other projects. So you can have MPI for DL, MPI for QML, MPI for Spark, MPI for Dask. So you take the MVAPICH, then take all these other modules. So depending on your need, you will be able to satisfy HPC need, AI need, big data analytics need. Okay, so that is our kind of the roadmap where we are going on. So the dynamic collective tuning. So this is what I think, let's follow up Dan's NVL72 machine with 11 interfaces and all. Okay, it's very hard. Okay, like unless we get a system, access, spend 6 to 9 months, we'll be happy to do that. We can't optimize the collective. So in the pen and paper, there are a lot of algorithms, but as you know, when you run on the system, okay, unless all kinds of variations come. And even though in the prior releases, we have done a lot of static tuning. Okay, so let's all to all on this topology, how it will work on this message sizes. So for last 20 years, we have been doing that. But then the question is, even on the large scale system, static tuning may not be beneficial all the time. Let's say you have a new job allocation, that job is totally spread out. So your topology is changing for that particular job. Okay. So the question is, can we actually do something as the job is starting to run? Can we learn from that topology, from the algorithms, message sizes? So that's why we call it like a adaptive, it combines the collective knowledge with real-time adaptive system-specific analysis. So there are algorithms there, but it automatically checks to see which algorithm will be the best for that one. So even though I am not like this NVL72, I think we can do an experiment here, okay? Okay? You give us the system, we'll directly run this feature and we'll see how close it comes to the static tuning, okay? So, so just to give an insight or have to a little bit fun, when you go to an ice cream shop, how many people sample first before taking? Many of you, right? So think of like that is a dynamic decision, am I right? You're going there, and you might have looked at this menu saying, I'll go for a blueberry flavor, but then you see, oh, there are so many flavors out there. You ask for some sampling, and then, oh, I'll go for this, I'll go for that. Think of that kind of knowledge we are trying to bring to them. Okay, so before the job starts, it actually does something, samples and all, and then decides, yeah, for now, for this job, these will be the best. Okay, it's a very new direction. We have just pushed this release. Of course, there is a lot of research needs to be done. We need to see how it will be effective, but I'll try to show you some numbers. So these are like a DAN systems, Vista, as indicated. So these are all numbers, like let's say this is a 64 node 32 ppn, static tuning versus dynamic tuning. So this is like the latency for all 12. See, sometimes you get big benefits. Okay, you just turn on. Like in fact, in the MVAPICH 4.1, it is default. You don't have to even do anything. You may need to turn off some flag to disable it. So we have enough confidence that this will work. So same thing happens, like a small message, medium message, large message, because many times these are the things which take so much time to tune. We have not done it, and we don't, like many times, you don't get even the larger system. Okay, TAC has been very kind. We work with them. We get some dedicated reservation for 256, 512 nodes for 5-6 hours. we run it. But this is the powerfulness of that dynamic tuning. I'm just trying to say. Okay? So that is there. So then let me give you some sample numbers. So I'll take some different combination. You remember I said like a vendor neutral. So let's say the frontier system, which used to be number one earlier, it has a AMD CPU, AMD GPU, and Slingshot. The second one is, of course, Vista. It is the Grace Hopper, NVIDIA GPU, InfiniBand. And the third one is the new direction is coming. And I think Dan indicated to this is the APU. Okay, the AMD MI300 APU. I'll go into more details and the Slingshot. Okay. So first of all, on the frontier, so this is also some new things we are getting engaged with the users. Again, I know many of you are vendors here. I respect everything, all of you. Many times when a vendor deploys a system, whoever is the organization, they put a lock saying, look, it is only our MPI will run. Okay. If any other MPI you support, our contract is void. Okay. But the end users want other MPIs, right? So this is where I think Frontier, they have started a new thing, what they call it like a UMS, user managed services, or I think user managed software. Okay. So Frontier started this. So actually we have that. So in fact, you can think of like we deploy and we maintain it. Okay. And the end users of the Frontier can actually directly put this load our module, and we continuously update it every time we make a release. So the end users of Frontier can directly use, and I know some of your stack is also there, Tower and all. So the Frontier is opening up that kind of a direction so that it is avoiding like any constraint with vendors or something. It gives the best options to the end users. Okay. So if you take a look at numbers, so this is on the Frontier, Cray and Pitch. That is the default because it is a Slingshot system. So here I'm trying to show some standard. These are the numbers taken with the OSU micro benchmarks, Cray and Pitch versus the MVAPICH 4.1. So you can see here it's like a intra-node, CPU to CPU. Lower is better. You can see like and the lower one is the bandwidth, higher is better. So we're able to give good benefits compared to the vendor supplied library, the Cray and Pitch. This is the internode. So the internode is again like since it's a Slingshot, we are mostly determined by the Wi-Fi layer, whatever they are providing. So, but we get a little bit of optimizations we have done. So you can see like a bandwidth, we are a little bit higher, and then the latency is more or less the same as a Slingshot. So then if you go to the collective, I'm just showing some sample numbers just to give you a feeling. So this is the GPU. I know a lot of debates are happening on all these collectives, GPUs, and especially all reduced for AI training and all. So this is actually on the Frontier. If you see there is a multiple users, and I think Dan, you indicated that also slide. Somebody can go here on the Cray MPI, Cray and Pitch they can use, or they can use the RICL. There's the AMD's RICL for all reduced versus our MVAPICH Plus. So this is the small, medium, large. You can see there is a wide gap. MVAPICH Plus can actually optimize. This is very much optimized for all reduced on this system. Okay. So if your AI workload is using a distributed training, you should be able to utilize directly our MVAPICH library. So let's go to the Vista, and I think Dan has seen some of these numbers I had said earlier. This very similar thing. These are on 256 GPUs on AMD Vista. So here, so we have not only MVAPICH Plus, we have, there were two nickel versions here. One is a default, like a nickel 219. But when we ran this experiment, it was 221. And I think yesterday, 227 or 228 has been released. So continuously, newer versions are coming. We need to redo the test. So this is like a small message, medium message, large message. And here you can see small, medium, we have benefits, and large, we are almost exactly the same as the nickel, but OpenMPI is not doing very good there, as you can see. Altogether is also another collective, which is getting very important on the AI workload. This is on the 256 GPU. So here again, we are able to get very good performance. And the very lowest one, I think here, OpenMPI is doing better. But as we go along the large messages, we are able to do better performance. And same thing is also like on the reduced scatter, which is another collective. So like this, as you can see, like for system-specific things, we have been able to optimize all the collectives at the MPI layer. We are able to give either competitive or even better performance compared to the other libraries. And this is a WRF code, pure scientific code. This is on Vista. As you can see, like as the system size is scaling, it's like a 32 node 144 ppm runs, around 5% better performance. We're able to give through OpenMPI, which is the alternate MPI library, which is available on this system. Now, this one is a new architecture, totally. APU, I think we heard yesterday, Gautam presented. So this is this unified memory. You can define a buffer, but that buffer can be accessed through CPU or GPU. Earlier, the CPU memory, GPU memory were separate. So this opens up lots of challenges, not only for the end users, but also the MPI runtime or any of the programming models runtime. Okay, so we have just started the scratch here. We have some initial designs, but we have a lot of additional designs in future. So you can think of all combinations. Okay, so for example, let's say I want to do an all reduce on a buffer. Should I do through GPUs or should I do through CPU, or could I also combine both of them? Okay, depending on the availability, like hybrid algorithms. Nobody has done this kind of hybrid algorithms yet. Okay, so like this, we have started exploring internally, but this is the initial release. We have some basic schemes which are there, and this is running on the San Diego Supercomputer Center, and we have some also access to the Livermore, but those are like more proprietary. I cannot show the numbers unless I get the approval, but the SDSC I can show. I think tomorrow there will be a talk by Mahidhar from SDSC. He has been very helpful to us. He will go into more details of this number. So you can see here again, like the latency, we are able to reduce 30%, 40% bandwidth we are able to improve. This is also like a one node, 192 ppm. So this is a very fat node. The CPUs, very similar kind of trend. You can see where MVAPICH Plus is able to deliver better performance. This is like a 32 node. That is the kind of the maximum configuration we have run there. They have only 42 nodes. Some nodes go down. Maximum 32 nodes. We'll be happy to run on larger number of nodes if we get access. So 32 node 4 ppm, like 128 node. CPU, similar things. And here we actually ran OpenFOAM, not just the collectives, but at the 32 node scale, here you can see like on an application level, we are able to boost 6%. Okay. And here, in fact, the right-hand side, even WRF V4 corners couldn't run even. So they're still trying to take a look at with the cramp. So it just gives very early system. We got access only for what, 6 weeks now on this machine, and we have been able to deliver a stack and with very good competitive performance. So this is something new. I think you heard yesterday. So the idea is that the GPUs, if most of you know, like they're being used for computation. But then when you try to communicate, let's say you are trying to do a lot of these AI workload, you are trying to do collectives, even point to point, you want to send some 1 gigabytes, 1 megabyte. Can I do on the fly compression? Okay, because that time, before the communication, if I can compress on the sender side and uncompress on the receiver side, even though it will have some overhead, but the message side may be significantly reduced based on the data. Okay, this is dependent on application. You cannot do blindly. It's just a compression. For some data, you will have very good compression. For some, it may not. So this is where we have done, like this is on the fly compression with MVAPICH Plus. So here we are showing it on the Vista, 128 nodes, and then that is the frontier. So this is an AMD GPU. This is NVIDIA GPUs. As you can see, like across, and within the MVAPICH Plus, there is this compression. We support GFP. So it is a lossy compression, and it has different parameters. You can actually tune. It's a runtime parameter. Depending on your data or application, you can actually see whether you have a rate 16, rate 8, rate 4, you can do, and you can see sometimes you get very big performance gain for these collectives. And this is another application. I think tomorrow there will be a talk from Ahmad from UTK. We have been collaborating with him. Even Samir is also involved. We have a joint NSF grant. Hefty. So the Hefty, as you can see, this is an application, which is an FFT application, and we're able to boost performance by 24%. Real end application, okay, using this on-the-fly compression. Then similarly, we're also working with Yifeng Kui. He will also present tomorrow. He's on the same project. These are a little bit older results. We have some newer results he will show. This is an AWP ODC, which is a seismic simulation. And I think, Dan, this also is one of your application, the tax application. Same hardware. Okay, we're not by changing the software, we're able to the left-hand side, the higher is better, the right-hand side is lower, the better. we are able to turn on this compression and then boost the benefit. Okay, so these are some of the techniques we have been using. We'll continue to use that more and then see how those results come out. So now moving into the AI workload, as I said, we have the base MVAPICH Plus, and then we have a lot of these other modules. Gradually, they're coming up. I'll just touch some of these modules. So, so the first one is I think Navras indicated yesterday. So this is we call it HiDL 2.0 release. So what we have broadly done, I think let me go to I think I didn't have that slide. Okay. So if you see the MVAPICH Plus, so mostly like all the AI training, you try to run with, let's say, PyTorch. Okay. So what we are saying, you don't have to change. Many times when I say MPI driven, they say, no, AI people will never use MPI. I'm not saying to use MPI. It's the runtime, okay, MPI will use. At a top level, you remain, all your applications remain the same. So what we have done is, in the PyTorch, when NVIDIA takes it through NICL, or AMD takes it through RICL, we are taking it through MPI. That's all we are trying to do. No difference. And in fact, this is a GitHub. We have opened it up. This is for the 2.71. You can actually download. And as some of you know, building PyTorch is very complex. Sometimes it takes time. So we are gradually introducing wheels on different machines so that you can directly take the wheels and then just try running. So we want to save your time. So we have wheels available on the frontier. We'll be able to have one for Vista. So that is how we are trying to enable this AI community, saying, okay, you can still run your applications without any changes, but you don't have to be vendor dependent for a collective library. So this is actually on the Vista. We are exactly matching with what NICL does. Okay, go up to 64 GPUs, and if we get some larger access done, we can run it on the full scale system. And of course, you can see, I mean, again, I don't know, Reach is here. We collaborate with NVIDIA and all, but NVIDIA has so many engineers working on optimizing NICL collectives. By the way, most of them are my students who have gone there. They're optimizing. That's fine. But we have MPI support. The current students are competing with the older students. Okay, so they have now better algorithms. They're able to have exactly same performance here. And same thing on the RICL. Several members of my team are also with AMD optimizing on RICL. But here we are actually giving 12% benefit compared to RICL. Okay, this is on frontier with 128 GPUs. So I'm just trying to show that, I mean, it's the same kind of a communication. Okay, it doesn't matter from the AI workload whether what is the stack it is going through at the end, as long as it is doing all reduce, all to all, scatter gather, all those collectives. That's what matters. Okay. So that is one direction we are going. Then the other ones, you know, those are the data parallel, of course, model parallelism. So this is where also we have been focusing on this like 1024 V100 GPUs. We're able to scale. And then here also now you can turn on that on-the-fly compression. So that gives you in more boost. We have not done a very thorough study recently. These are a little bit older results. The field is moving so fast. So here again, that all-to-all with compression, there is this is a PSDNS, which is the left-hand side, which is the scientific simulation. We can give you 30% benefit. And this is the deep speed from Microsoft. We did this for the ISC paper. You can get like a 35% benefit. Okay, if you turn on the compression, in fact, your communication latency reducing, your collectives are running faster, so you get better things. So these also same all reduce on the ISC last year. We presented. So all these solutions are available in MVAPICH Plus. You can download and you can build our PyTorch and take the runs, and we'll be very happy to work with you on this. So then what we have done, still this debate between MPI and NICL/RICL is there. So we have introduced this called a mix and match runtime. Okay. So even though it is an optimization world, by the way, I mean, for any system, whether you go through NICL or MPI, for that GPU, that configuration, you have to optimize. So what we provide here is a very quick software stack, which can actually do some sampling. Again, if you run with MPI, run with NICL, let's say for 128 bytes, MPI is good, but 2 kilobyte NICL is good, it will mix and match. Okay, So it is saying, okay, now for this kind of traffic, I'll use the MPI substrate. For this kind of thing, I'll use nickel substrate. Okay, so we are allowing that. So again, then the people are trying to get the best performance here. So you saw this then yesterday, this was like a large high resolution images. So that is also a newer field which is coming up, very high resolution images. How do you do the training? So this is where like a lot of these newer parallelisms are coming, layer parallelism, pipeline, spatial layer. So we saw some results yesterday here. So compared to like to let's say here we have a spatial parallelism and you use spatial plus bidirectional parallelism, we are able to push. So gradually all those solutions will be pushed so that people can actually use not only the data parallel, but also model parallels, hybrid parallels. So let me move to the OSU micro benchmarks. As many of you know, many of you would have used it. This has been there since 2004. So when initially we had the MPI library, of course, people knew in the 2000 how to evaluate performance of an application level, but there was no real benchmark to evaluate at an MPI layer, like how much send receive takes, how much time the collective takes and all. So IMB was there at a very early stage. There were a few other runtimes. So we tried to introduce this OMB, OSU micro benchmark. It has been continuing again for the last 21 years. The latest release is the 7.5. And of course, in our MVAPICH as well as MVAPICH Plus, OMB, we get a lot of patches. As you know, some of you know about our MVAPICH Discuss. People contribute patches, we take it. People are asking like to directly have source code access. OMB is open source, but it's a tarball, not like a GitHub kind of thing. So that is the new direction we are trying to do. There are two things happening. Nat yesterday talked about this. OMB, even though it has a lot of features, you have to run individually multiple tests. Okay, so we are trying to improve the runtime. It is similar to like IMB, so that it will be much more easier to not only run, but also make changes. Because now the source code is very separate, like for each of the collectives, we have separate point. So if somebody's a feature request is coming, we have to actually put it on all different places. Okay, so it is taking over it. So this is something new. We are totally refactoring the MPI benchmarks. So reduced files, less duplicated code, easier patches, and it will be similar to like IMB all in one test. And you can actually run multiple tests from one MPI launch command. That is the thing. So you can run MPI exec, then you say, okay, I want to run this benchmark 1, benchmark 2, benchmark 3 kind of things. Okay. So, but it will remain backward compatible. So we are not changing anything. And then we'll try to open up. Okay. So that is the next plan, may happen in the next might be 2 months or something like that. Just like we'll be very happy to work with the community, and then people can have direct contributions, GitHub access. Of course, we'll have licensing, all those kind of issues we need to take care. Everybody's IP is protected, but that is the direction which we are going. I just want to indicate that. So let me quickly move, and then so now with the MVAPICH 4.1 Plus is available. So the open source version of the MVAPICH 4.1 is being worked out. Might be in the 2-3 weeks. We got slowed down because of the mug, but we'll be have that released soon. But this is the MVAPICH 4.2, which is coming. So this is where again there is a lot of focus on all these enhanced GPU support, especially the APU support will be there. This compression. Currently, we only have like a GFP and MPC, but we want to make it very generic. If you have any other your compression library, you should be able to also utilize it. Okay, so that is the kind of things we want to open up. And of course, the SARP collective support, SARP has been there for NVIDIA for many years. In our MVAPICH 2.37, we used to have all the support, but then once we moved to MVAPICH 3 and 4, that's what I was saying, though some of the older designs are still there. We are trying to bring them back. So we'll have the SARP support in the new release. Now, while this is going on with all the GPU, as you know, FPGA is also catching up. Okay, so this is where, just like CUDA or MPI, like how do you send data from directly GPU to GPU? We have an actually internal paper, and I think Nick presented. I forgot to edit it. So we have actually think of like a FPGA aware MPI. Okay, so we are trying to bring that kind of support, and then We have also been working with CXL. I mean, we have been having some discussion with Srijit and Fabrica and other companies. As you know, the CXL standard is actually allowing at least the scale up, okay? With providing a lower latency, you can get better than the compared to main memory, you can have disaggregated memory. So here, what we are trying to do, again, this was the last year's work I want to show. It is more like an emulation. We have gone through emulation. There is a KMU emulation, some of you know. So that is the direction where we have gone. Of course, in Fabrica hardware, they are showing. CXL will be very happy to test with it. So what we did last year, in fact, we are also collaborating with our A3 colleagues who are sitting here on a joint paper. We had PERC last year. We presented. So we took the KMU mode and then trying to say, okay, how much CXL can provide benefit? It is an emulation, okay? So that's how we are able to do here. If you see, just like GPUs, you can get host to host, host to device, device to device, device to host. Then, of course, so here we were able to show for any of these numbers. So we had an emulated MPI over CXL versus MPI emulated MPI over Ethernet. And we're showing that CXL performs better for small messages. But then in the KMU emulation, there is some limitation. So this is where the bandwidth is not strictly coming out, the benefit, and we're able to show that, okay, CXL with shorter communication paths outperforms Ethernet. So with this, let me conclude here. So it just shows we have been in this field, as I said, for the last 25 years, and thanks to support for this community. And we have been providing the high performance MPI solutions for all the different CPUs, GPUs, interconnects, and the new MVAPICH Plus is trying to provide that converged software stack. I provided an overview for HPC and AI big data. Thanks to all this funding and equipment support over the years, otherwise we could not be doing all these things. But last but not least, these are all the greatest people. I think what I showed here in 68 slides is actually work of 25 years of a lot of these students. And if you go back, look at some of the names, most of these people are in all top places, in all different companies, national labs. So I still want to provide credits to all of them. The more important thing I'll also want to indicate, as you know, Hot Interconnect is starting tomorrow. So we have one paper. This is a very interesting paper. Last year we had a paper. How do you actually characterize the communication pattern for training? This year we have a paper on communication patterns in distributed LLM. Okay, so we have very nice analysis there, like how the inference workload will be working. So please feel free to join that tomorrow. And we also have 2 tutorials on Friday. One is on the high performance the deep learning side, and of course another one is the high performance networking side. Okay, so we'll provide more details on there. So with this, I'll close here. I know I took a little bit more time, but I'll be happy to answer any questions now or later on. Thank you. Any quick questions? Yes, please.
As usual, of course, very impressive work. Just quick question on the CXL. You're looking at as a CXL as a GPU to GPU interconnect there, or memory?
No, here it was pure memory evaluation kind of things. So what we just trying to do, like this was like the test bed. We had like 2 x86 compute nodes with 4 cores each. It was interconnected by Ethernet, and then we were just trying to see if we replace that Ethernet by CXL, how much benefit will be there. These are very preliminary one. Now I think there are a lot more hardware support. We have some more things we are trying to, like if you take like the Blackwell architecture, there are so many cores, we can actually emulate more. So we have some inside results which are coming out. But we'll be very happy to work with all the vendors and then see whether we can really take some good numbers. I know that will be very interesting to you. Yeah.
Maybe just a follow-up there. So on the scale-up side, you have option for, at least on the Grasshopper or any VLSIM, whether you can go through load store or whether you can do any kind of send receive channel semantic. I'm wondering whether if there is any data or work that you guys are doing to compare that, or maybe it exists already.
So when I talked about these collectives, I mean, so there actually we have optimized over NVLinks and all. Okay. So I showed on the Vista. Vista unfortunately has only 1 GPU per node, but we have tried running on like the Isambird on the UK. They have 4 GPUs. Frontier has 8 GPUs. That is their equivalent in Infinity Fabrics. So we take care of the whatever is the existing scale up. Like NVLink, we are able to take advantage of that. So that's how we are able to actually, if you see those numbers, they are very competitive, and even Recall and all, they are able to do better. But we have not reached to scale-up Ethernet. I was talking to Hemal yesterday. I mean, if we can get access to those kind of things, or UL link, as Dan said, these machines are becoming very so expensive. I can't afford unless there's some big grants or some big collaboration going on. But we are ready. As if you have this kind of machines, we'll be very happy to evaluate, show the numbers, optimize. Okay.
So
Yes, yeah.
a bit of follow-up on that, right? So actually, one of the things I was trying to understand is the dynamic adjustment that you were talking about. Like, I mean, the most optimal answer requires you to go sort of to go where Manoj was going. You would have to write CUDA at the bottom, or you'll have ROCm at the bottom or something, because even whether you're doing scale-up Ethernet or something else, at the